Welcome everyone to the 2023 Photonics Spectra Conference. Thank you for joining us, and in this session, you will hear from Chris Russell, a Senior Field Application Engineer for Universal Photonics. Chris, in his time at Universal, has been instrumental in developing the R&D side of the Quality Control Lab. Today, he is joining us to discuss the process of lapping hard optics. If you have any questions or comments, you can type them right into the conference chat box that is on your screen. And if you missed part of today's session, you can always come back later and watch it on demand. If you have any sort of technical issues throughout the event, please log out and back in to rejoin the session. Chris, we appreciate you for taking the time to present here at the 2023 Photonics Spectra Conference.
Thank you very much, Jacob. Appreciate it. My pleasure to be here. So today we're going to talk about coolants and trisect, how processing variables positively or negatively affect the lapping process. So if you're not familiar with Universal Photonics, just want to give you a little background. Our core business is precision surfacing and polishing materials. We're a global brand that was established in 1926, so approaching the 100-year mark here. We have 3 manufacturing facilities, which are all ISO 9001 and 2015 certified. There's Universal Photonics, our corporate headquarters, which is located in Central Islip, New York, where we produce proprietary polishing products, including pitches, compounds, abrasives, polishing slurries, impregnated media, and as well as some equipment and machinery. Next is our J.H. Rhodes facility, which is located in Vernon, New York, just north of Utica. And that's where we produce our LP Unilon polyurethane polishing materials, as well as J.I. Morris polishing pads. The third is our Nuvite chemical compounds, and that's also located in Central Islip, New York, but it mainly specializes in appearance maintenance products for the aerospace and airline industry. So bound abrasive lapping, aka fixed abrasive lapping, is becoming more commonly used in the precision optics industry. So these processes can be more complex than traditional free abrasive lapping processes. So it's important to understand how process parameters affect your process, including coolant type, working pressure, usage of a conditioning particle, and platen speeds. So in this study, we will show how changing each variable can positively or negatively affect your lapping process. So fixed abrasives contain abrasive grains that are bound together by agents such as binders, fillers, or other forming agents into defined forms. So typically there are 2 types of processes. There's the conventional fixed abrasive lapping, aka pellet lapping. So in this process, the diamond or any other abrasive is incorporated into small pellets, and those can be either metal, vitreous, or resin bonded, which are attached to cast iron machine platens. So the second is structured fixed abrasive pad lapping. So this process consists of an organic polymeric binder and an inorganic abrasive mineral, in this case diamond, composite, which is formed into a structured 3D pad. So in this presentation, we will be discussing structured fixed abrasive pads, in particular, the Trisect 677XA pads manufactured by 3M Corporation. So if you're not familiar with Trisect, I just wanted to give you a little few images. On the left here, you can see the Trisect diamond tile attached to the bottom plate of a double-sided lapping machine. Just zoom in here a little bit so you guys can see it better. Then if we move a little bit to the right, you can see we zoomed in. You can see the individual tiles there. The typical Trisect size is 2 millimeter by 2 millimeter by 0.8 millimeters thick. So if we zoom in even more to the microscopic view, you can actually see the diamond agglomerates coming out of the surface of the tiles, or what we call the features. So swarf is very important for most fixed abrasive lapping processes. So most fixed abrasive lapping pads are designed to wear slowly from glass chips, which is also known as swarf. So the swarf formed during lapping serves to wear the pad and to expose fresh diamond. Without the swarf, the diamonds will slowly dull. Eventually, your removal rate will drop to close to nothing, but your surface quality would be very good. On the other hand, if you have too much swarf, the pad will wear too fast, and the cost of ownership for the pad becomes too high for most companies. So it's important to note that hard to grind materials such as ceramics and sapphire do not generate swarf large enough to cause pad wear. So a conditioning particle must be used in conjunction with the coolant. So coolants assist in the fixed lapping process in a few different ways. They provide lubrication and decrease surface roughness or scratching. They also help to suspend swarf and to increase removal rates through higher pad wear. So in these trials, we tested various coolants from different manufacturers, all at a 5% concentration. These coolants are Saberlube 9016 from BASF, Microcut 28S from Integris, Diamond Cool and Blue Cool from Universal Photonics. And we also wanted to study the effects of a pure suspension agent. So we have a suspension agent that is in R&D at Universal that's actually made for a completely different application that contains no wetting agents, no lapping fluids for lubrication. So we wanted to study what the effects of just suspending the swarf would be on the lapping process. So to give you a background of our testing, all of the testing was performed on a double-sided lapping machine. Each trial was run for 60 minutes. The machine we used in particular is the Somos TPM 400A lapping machine. And the removal rate was measured every 10 minutes. The surface quality was averaged for the last 30 minutes. And all processing parameters were kept constant except for one. So those varied parameters are coolant type, the working pressure, the usage of a conditioning particle or no conditioning particle, as well as the platen speeds. Okay, so if we want to take a look at our first result, this was the trial where we wanted to see the influence of the coolant type. So basically, again, we kept everything constant in the process except for the coolant type. And we ran, you can see 60 minutes on the left there, which is the removal rate. And the important thing is this is on BK7 glass at 1 pound per square inch pressure. So later we're going to discuss how pressure influences the lapping process. So just keep that in mind. So you can see if you take a look at these results, in general, the Saberlube was the most consistent and had the highest removal rate. The Diamond Cool, on the other hand, had the lowest removal, but it did have the best surface quality with a PV of just under 1,000 nanometers. But for pretty much all the coolants, the removal rate dropped for the first 30 or 40 minutes, but then stabilized. The pure suspension agent had a mediocre removal rate, and it did have an unusually high surface roughness, probably because that removal rate was pretty low. So now we ran fused silica using the same process conditions, again, keeping the pressure at 1 psi and all the plate speeds the same. And we wanted to see how the coolant type influenced that particular lapping process. As you can see, contrary to the previous results, actually in this case, the suspension agent, pure suspension agent, had the most consistent and the highest removal rate, but it did have the highest surface roughness. The diamond cool and the blue cool and the microcut had excellent surface quality, and the removal rates for those materials were lower as expected. Again, the removal rates generally stabilized after 30 or 40 minutes for most coolants, really except for the blue cool, which kind of took a drop at the end. So now we ran fused quartz at 1 psi, and surprisingly, our results were a bit different than for fused silica. You can see that the suspension agent had the highest removal rate, but the highest surface roughness as well. The blue cool and the microcut had extremely good surface quality, but again, lower removal rates. It's can be extremely useful. Just want to put a side note that getting surface roughness this low is extremely useful if you want to measure flatness on an interferometer before going to polishing. So this, if you're really fighting or trying to achieve a excellent surface flatness, you know, in your lapping and polishing process, it could be extremely useful to have an idea of what your flatness is heading into polishing, to make sure that you're not trying to do the shape change in polishing where the removal rate is slower. And you can see with this process that the removal rates dropped steeply for all coolants, but again, they somewhat stabilized eventually. Okay, so next, the fourth material we tested to see what the influence of the coolant type was sapphire. It's important to note that this is C-plane sapphire, and this is actually Trizac 20 micron, which all of our previous testing on the glass was Trizac 9 micron. Also, as I mentioned earlier, sapphire and ceramics tend to not wear the Trizac pad well enough on their own from the swarf. So we did use a conditioning particle of 0.5 weight percent, microgrit WCA 15. So you can see here that diamond cool definitely had the highest removal rate. And as expected, it did have a slightly higher surface roughness. Again, you see kind of a big drop. It looks big on the chart anyway, but we're only talking a few microns. But generally, the removal rates were somewhat stable after the 30-minute mark. So now we wanted to take a look at how the working pressure in your process influences the lapping process using Trizac. So on the chart on the left, you can see the chart from earlier, which is the BK7 at 1 psi removal rate plot. And on the right, you can see the same plot, but for 2 pounds per square inch working pressure, and again with BK7. So you can see that once we switch to 2 times the pressure, generally most coolants had 2x the removal rate, or pretty close to it. Sabre Lube was still the highest removal rate, but you can see how consistent that removal rate is from the 10-minute mark all the way to the 60-minute mark. The process was very stable. Diamond Cool again still had the lowest removal, and generally the removal rate stabilized after 30 or 40 minutes for most of the coolants. But across the board, generally higher pressure was more stable, you know, as time went on, as compared to the same coolants working with 1 pound per square inch pressure. So now if we take a look at how the surface quality changed from going from 1 pound per square inch to 2 pounds per square inch, very interestingly, increasing the pressure lowered the surface roughness almost across the board, minus the suspension agent. You can see that pretty much the Diamond Cool, Blue Cool, Microcut, and Saber Lube were all under 1,000 nanometers. Generally, all those were shiny enough that you could use a interferometer to see the flatness on them, which again, I mentioned is, I think, particularly useful. And Saber Lube at 2 psi was the real winner because it did have technically the best surface quality as well as the highest removal rate. It's kind of a rare best of both worlds. Okay, so again, we wanted to take a look at the influence of the working pressure, but this time with fused silica. So on the left, you can see the removal rate for 1 pound per square inch. And on the right, you can see the removal rate for 2 pounds per square inch. So actually, the suspension agent was probably the best at 1 psi, but the other coolants caught up, interestingly enough, once we increased the pressure. So, and as well, you can see on these plots on the right that the removal rate was much more stable at 2 psi. So it seems for both glass types running at a higher pressure seems to be more stable for your process. Okay, so if we take a look at the surface quality results, more predictably, increasing the pressure increased the surface roughness almost across the board. Again, minus the suspension agent, which was kind of the one outlier. Diamond Cool actually still had the best surface roughness at 2 psi and was just a slight bit lower than the rest of them. So the third trial we wanted to run was to see the influence of a conditioning particle when running, glass. In this case, fused silica. So basically, we ran the exact same process, using Trizac 9 micron, and then we ran it with no microgrid, and then we ran a trial using microgrid at 0.5 weight percent, and it was the WCA 5T. So the green plot on the top, which includes the conditioning particle, you can see how stable the removal rate came over time. It started off at 60 microns a minute and dropped down to 50. And generally, after that first 10-minute mark, it really pretty much stabilized. Using a conditioning particle does require constant mixing of that powder and the coolant. It's important to note that. The surface roughness did increase a little bit, roughly 2x, when we added the abrasives or the conditioning particle to the coolant. I think adding a small amount of abrasive, if it's okay in your process, can help you achieve the best of both worlds, being a very stable, high removal with still an excellent surface quality. So as I mentioned with ceramics and sapphire, we generally do not run without a conditioning particle, but we wanted to do a test to see how the weight percent or the amount of conditioning particle we added to the coolant would affect your lapping process. So you can see, again, this is with Trizac 20 micron. This is C-plane sapphire. And the conditioning particle is microgrid WCA 15T. And we varied the weight percent from 0.5% to 1% and to 2%. you can see that, interestingly enough, the 1% and the 0.5% kind of followed the same path as on their removal rate, in that they started, relatively high at 10 minutes, dropped down at 20, then kind of bounced up and did a little, kind of sinusoidal curve. But you can see that again at the 2%, that the removal rate was pretty stable over time. It only varied by about, 1 or 2 microns. So that's particularly interesting to note. It didn't necessarily, though, increase the removal rate, from adding 0.5 to 1 or to 2. In general, you can see that towards the end of the process, the 0.5 weight percent was pretty similar to the 2 weight percent. And you can see on the right that the surface quality was varied, but it was generally pretty close regardless of the conditioning particle concentration. So the last test that we wanted to run was to see the influence of your plate speeds. So again, we kept everything constant except for the plate speeds, and this is the top and bottom plate of the machine, and the RPMs. We kept the directions constant, and we kept the gear speed and direction constant. So the removal rate was consistent and somewhat linear. You can see that, I think you could show it's pretty much a straight line down. The surface quality varied depending on the plate speed, but again, they were somewhat similar and there was really no trend. It was kind of a little bit all over the place, but again, somewhat similar. And again, this was back to using Trizec 9, and we did use Diamond Cool at the 5% concentration for all these trials. So if we wanted to give a summary of our observations from these trials, we could say that increasing the working pressure increases the removal rate, but it also can increase surface roughness. The real contrarian to this thought was the BK7, where we increased from 1 psi to 2 psi and all the surface roughness is improved. We thought that increasing plate speed increases the removal rate, but doesn't significantly affect surface roughness generally. The coolant selection for each material type is critical. Remember, if you're looking for high removal rates or best surface quality, generally it was pretty different from material type to material type. And adding a conditioning particle increases the removal rate generally, but it can also affect surface roughness. So, one thing to think about is that the process choices that you make based on our trials or using the data from our trials are dependent on your desired results. Some customers want low surface roughness, generally to improve polishing times. Others want high stock removal to lower the lapping times if you're really trying to hog off a large amount of material to reach your critical thickness, center thickness. Or maybe some customers want low pad wear for lower cost of ownership of the pad to really extend the pad life. Again, personally, I think the ability to measure flatness on a standard interferometer prior to polishing is very important if you're trying to achieve tight flatness requirements. So again, keeping that in mind, low surface roughness would be an important process goal for your lapping. So we just wanted to say that in the future, we're looking to expand our studies. We want to run fused quartz trials with the conditioning particle. We want to run more testing on these materials at a few more working pressures, possibly go a little bit higher than 2 pounds per square inch, and test additional materials. We're looking at calcium fluoride, zinc selenide, germanium, as well as silicon. So if you have any questions, feel free to call, email, or text anytime. I appreciate your attention, and thank you very much.
Thank you so much, Chris, for sharing your research and work on hard optics. We do have time for a couple questions here, but before we get to those, I just want to remind everyone in the audience, if you haven't already, you can type your questions and you can type your comments into the conference chat. And if you haven't been answered, you'll be reached via email at a later date. Chris, how does your results compare to traditional free abrasive lapping with alumina on cast iron?
So generally, the removal rate for Trizact was about 4 to 5 times faster, but interestingly enough, the surface quality is pretty similar, especially for higher pressures. The Trizact was generally all around better at lower pressures, so like 0.51 or 1.5 psi, and that was roughly like 4 to 5x the removal rate for Trizact and about half the surface quality.
How do you measure that surface quality?
So we have a Zygo NewView 8300, I think it is, and we use a 10x objective, and we generally use 0.5x digital zoom on it.
As you get more comfortable doing this and you get a little more research about what is happening here, what is your goal as you aim to kind of improve this lapping process?
So again, I personally think, a lot of times we generally don't struggle with coming up with a process for good, high removal rates or good surface quality. But generally, I struggle with trying to achieve high flatness requirements for a lapping and polishing process. So generally, I think that being able to measure the flatness, again, I know I mentioned this about 5 times in the presentation, but being able to measure the flatness on an interferometer before going to polishing to make sure that you're not fighting, a bad flatness in polishing where your removal rate's low is extremely beneficial.
Gotcha. I think we have time for one more here. Do you have any measurements of subsurface damages for these trials?
So this is something we've actually thought about, and unfortunately, we do not. But we don't have a good way to measure this in our lab. But we like to think generally that the PV, the peak to valley surface quality measurement, is kind of like a predictor of subsurface damages. But we don't have any direct measurements, and this is something we're looking to do in the future on future trials.
Gotcha. Chris, we appreciate you sticking around for a couple extra minutes to answer some questions. Before we take off, I just want to remind everyone that this session is hosted by us at Photonics Media, and we certainly hope you're enjoying the 2023 Photonics Spectra Conference. Lastly, I have to say it one more time, thank you again to Chris Russell for presenting the effects of coolant on fixed diamond lapping pads when processing hard optics.
My pleasure. Thanks, Jacob.